Hello, everyone. I'm Rosie Howard, and I'm a research associate with Sara, and today I'm going to be giving an overview of the data cleaning pipeline developed by the EcoFlux Lab and affiliates. So first, I'm going to cover the items in this outline. You all hopefully received an email with a link to the documentation. Sara can maybe put that in the chat again. And these are also live links to that documentation for your future reference. And this presentation is available. So lots of places to get back to this. And so these items match the sections in the documentation. And I'll also provide links throughout the presentation where relevant. So as Sara mentioned, following this overview, I'll be doing a live demo with a step-by-step working example. I've put the data and template files here with a link, but it's also available on the website to download during the tutorial. So I can show you that a bit. So a bit of motivation to get started. We likely all know the many challenges involved in collecting and processing covariance data. So these include, excuse me, site selection, choice of instrumentation, manipulating large high-frequency data sets, also post-processing this data and implementing quality controls so that you can rely on these data sets. So our pipeline, what we're talking about today, is focused on post-processing and quality control. So our approach standardizes data sets and allows reproducibility for quality control, for gap filling of data, and for CO2 flux partitioning. And the intended result is that the minimized errors enhance reliability and expand usability of the data, overall enabling integration of diverse data sets into global networks for wider use. And note that high-frequency data processing was covered yesterday, and the recording will be made available for that. So a couple more notes. The pipeline and tutorial today is focused on 30-minute frequency data, so not your high-frequency data. And if you don't have your own data for the tutorial, as I mentioned, we have some provided for you to follow along. Also, if your data has a different averaging period, the pipeline will also work with that too. And users of the pipeline only need to have minimal coding skills. Essentially, you need to just edit some initialization and configuration files, and these provide the pipeline with necessary information on your site or sites. So here's a link to that documentation, if you didn't have that already. So while there are many online resources that can help with all these challenges, here we're focusing on the approach that the EcoFlux Lab uses for flux data post-processing and QC/QA. We've listed some other resources there for you. So in terms of required software, the pipeline scripts are written in Matlab, so you'll all need to have that installed, and we're recommending version 2023B and higher. We are planning for future versions to be open source, but for now we're working with Matlab. You'll also need to download our biomet.net Git repository. This library contains some scripts and functions for running the pipeline. And then later, I'm also going to show you how to configure this repository to work with Matlab. You'll see that in the tutorial. R and RStudio are also necessary for the third stage processing and one of our visualization tools that you'll see in a little bit. And then optionally, you can install Git and create a GitHub account, but this is only really necessary if you actually want to contribute code to the pipeline to biomet.net. And it's also optional to have Python for the high frequency data processing and methane gap filling. And there's some links there to some Git repos for those. So just another note on the biomet.net library. You can go to this link here, click on code, the green code button, and download the zip file. Alternatively, you can use the git clone command if you have Git installed, and then use the HTTPS or SSH protocol. And the configuration will be covered later in the tutorial. And just a note, if you do download the zip file, you'll need to rename the directory from biomet.net-main to simply biomet.net. Otherwise, you'll have trouble with things running. All right, so before we get into some data cleaning principles, I'll just mention what kind of data the pipeline is set up to receive as inputs. So you can start with 30-minute flux data, for example, some EdiPro output from a Lycor CSAT3 system, as an example. You might also have some 30-minute data from a separate MET system, meteorological system, such as a Campbell Scientific setup. And also some auxiliary data, such as site metadata and field notes and things like that you want to keep for documentation. So the tutorial today includes the EdiPro Campbell Scientific data. So assumes either you have that set up with your own data, or you can use our sample data. And if your setup is different, you can ask during the tutorial and breakout sessions about how to ingest your own data formats into the pipeline. So just note that, as I mentioned earlier, other averaging periods will also work. And the pipeline is designed to ingest basically any kind of data format. Yeah, I just mentioned these two because that's what we're using in the tutorial. So we want to just remind you of the data cleaning principles we're using. And these are important to keep in mind as you go through each cleaning stage. So the first stage principle, the idea is to keep the best measured data from each sensor. So you should have one trace per sensor and carrying out quality control on each of those sensor outputs. And this includes min-max filtering. So for example, for a temperature trace, you should use the climatology of your site to apply minimum and maximum temperatures. And there's also some calibration and spike filtering that you can do in the first stage, although we won't be covering those in the tutorial. You could potentially ask about them afterwards. So the first stage also includes assigning consistent Ameriflux variable names to standardize the data ready for the next cleaning stage. And just a note that there's no gap filling in stage 1, so this comes later. And then finally, the first stage prepares output for stage 2 with data saved in a specific format. And I'll talk a little bit more about that when we go through in the tutorial. So moving on to the second stage principle, you want to keep the best measured data that represents each property or variable. So for stage 2, you're essentially modeling the data based on the best first stage sensor output that you have. And you can do this by combining 2 or more variables to create one new trace. These input variables must have already been defined and cleaned in stage 1 already. So there are multiple ways to achieve this variable representation. You can average 2 or more traces, or you can gap fill your trace using data from a nearby climate station, for example. So the example on the right there shows air temperature at the bottom already passed through stage 1. And then the top trace shows that how this has been gap filled by data from a nearby climate station. And then it's also automatically preparing the output for stage 3. So moving on to the third stage, this includes a U-star filtering, gap filling fluxes, and met variables that still have gaps after stage 2, and also CO2 flux partitioning. So to do this, we use the ReadyProc package, and we've adapted this for use in Matlab, so you can basically work exclusively in Matlab. And for gap filling, you have a choice of methods. So the marginal distribution sampling, which is the default. And also you can choose to use a random forest approach. So again, I'm just showing an example on the right here. With any from stage 2 on the bottom, and then gap filled using the NDS method on the top, leaving no missing samples. Excuse me, I need to have a water. And then also want to mention we have an Ameriflux stage where relevant data is formatted for submission to Ameriflux, which is where we submit our data from our team.
Question, does Ameriflux want you to do U-star filtering or no?
No. So this data submits. So if you do the submit Ameriflux or any sort of base-in format for any network, it's not going to apply the U-star filtering to that. But you'll have U-star filter data for your own purposes. Yeah.
Okay, so we now get into the setup. First of all, you're going to need a main project folder, and this will encompass data cleaning and analysis for a particular flux site or group of similar sites. And yeah, you give this project folder a relevant name, sort of related to your project or sites as a whole. And then the functions to create the directory structure needed and to configure this structure to work with Matlab are provided for you in the biomet.net library that you will download if you didn't already. And these are the two functions, the names of the two functions that you'll use, and I'll go through those in the tutorial and what arguments they need as input. And then the result of running these is that immediately under your specific project folder, in this case, my micromet, you'll have new folders called database, Matlab, and sites. So just briefly, I'll go over what's in these directories, or a couple of things that are in these directories. So in the sites directory, this is where you're going to put your raw and cleaned data. And that's going to remain untouched and stay there without changing it in any way, because we want to be able to reproduce this process at any time. So that keeps it untouched in that directory. And then in the database directory, sort of buried kind of deep here, you'll see site ID. So this will have your site ID as a name, and that's where you're going to put your site-specific INI configuration files. And then ultimately, no jumping ahead, but ultimately this database will also contain your initial database created from the raw data you put into sites, and then eventually further down the line, your cleaned data. We'll get to that later. So I've just included a summary of the next steps that I'm going to cover. So sort of an overview of the 4 main steps you'll carry out. So firstly, as mentioned, you're going to put your raw data into the sites folder. split up by site ID and then data type. Then you're going to create a new database from this raw data by editing and running a Matlab script that we're providing. And you just need to input your project path, site ID, and raw data file names for that script. So next, you're going to rename and edit your INI templates that we're also providing. And for this, you need some site info, site metadata, original variable names, and a few other related parameters. And then finally, you will clean your data in Matlab using this function here. So it's just one command to run the data cleaning. And ultimately, this will give you your cleaned and standardized data ready for submission to regional networks, such as AmeriFlux. So a few more details on creating the database. As mentioned, you're going to add your raw 30-minute data into the sites folder, organized by site ID and then data type. So Flux and Met. For this example, you may have other data types too, from different measurement systems. And you can ask about those in the tutorial and breakout session if you have that. Next, we're going to copy the Matlab code to create a new main Matlab script. And all you're going to need to edit are the yellow highlighted parts in that script on the right. And we're going to go over this section by section in the tutorial. So this script will first create your database, then eventually you can add further code to carry out all the cleaning stages. So it will become like your do-it-all main script. So once you've run that new Matlab script, provided everything runs smoothly, you should see some output in your database folder. And the data files created are grouped first by year, then site ID, and then data type. You should see the variables listed under there. And we recommend inspecting your database at this point, and actually at every stage of cleaning, using the visualization tools that we're providing. And they're going to be talked about in a little bit, as I mentioned. So the next step is to create your INI files to configure the data cleaning. And you'll obtain the INI files from the website during the tutorial, and you're going to copy them to your database site-specific folder, and make copies and rename with your site ID. And I'll show you that again in the tutorial. So I'm just going to go over each of the cleaning stages in turn briefly. And so to recap, you put your raw data in the sites folder, created a new database. Within your database folder where the variables have the same original file names. And then within your first stage template INI file, that you renamed with your site ID, about halfway down, you'll see traces that look like this figure. So this section of the file relates to meteorological variables, and that's where you're going to put your input. You're going to input your metadata variable names. So in this case, we're taking our 2-meter temperature measurement that we want to represent our main temperature measurement. And we're inputting the file name here into input file name. And then also you're going to want to edit the sort of peach highlighted fields as well. So give your trace a descriptive title, start date of measurements. This is the folder where the data exists in your database. You'll want to check the units and then add any instrumentation information, such as the serial number and instrument model. And then importantly, you're going to need to edit this min-max parameter. And so this is related where you want to insert information related to the climatology of your site. And so it will filter and remove temperatures outside of that range. And then just a note that the variable name there is in AmeriFlux format using those positional qualifiers. So once you've added a few variables, you're going to run the first stage cleaning in Matlab using this function. And just to note the inputs, you've got your year of data, site ID, and then for first stage, you have a 1 with the last input argument. So for the next step, you're going to add what we're calling include files, or what are called include files, to your site-specific ini file. The include files that we provide already contain the core information for relevant data variables from a 4-component radiometer, such as a CNR4, and also from an EC system with EdiPro output. So the idea is that this saves users time, sort of writing and repeating lines of code for every single trace where typos and errors can get propagated. Oops, yeah. Okay, good. So how are we using these include files? At the bottom of your first stage ini file, you'll see this code block. And so, for example, for your radiation variables that we want to include this rad first stage include ini. And so we need to uncomment that. And so we're going to remove the percentage sign only. This file is read by Matlab, and that's how you do make Matlab comments. So you want to leave the number sign or pound sign. So and then near the top of the ini file, you're going to, as with the sort of metadata, you're going to add in your raw variable names into these lines of code where the yellow highlighting is. So then once again, after adding the radiation include file and adding the variable names, you'll run the cleaning to test this. So following that, we'll add the EdiPro include files. So for all Ergo systems or setups, we'll use this common file, regardless of what kind of Ergo it is. And then depending upon the ergos that you have at your site, you'll comment the relevant files beneath. And again, I'll show you that in practice. And generally speaking, we ask that you, or recommend that you do not change the include files that we provided for you. So yeah, once you've included your EdiPro include files, you'll run the cleaning again to test that. With the same command. And then finally, if you want to add your own other variables that aren't already in the include files, anything you want to use in your own analysis, and anything you want to submit to AmeriFlux, you can add those for other networks. So the good news is that once you've completed the first stage edits, so most of the work has been done. So moving on to the second stage ini file, the template we provided already contains the fundamental climate variables and minimum required variables to go on to run the third stage. So here's a snippet of the second stage ini on the right. So we're first defining a second stage variable name, and then we're saying for that variable, evaluate this statement. So it says assign this variable from stage 1 into this variable from stage 2, and yes, it has the same name, but essentially any variables on the right hand stage of the evaluate statement must come from stage 1, and so they must have already been defined and cleaned in your first stage ini file. And then even though in this sort of most simple case, we're not changing any of these variables, we still have to include this trace here, or it can't be passed through to the third stage. So just a couple of features in the second stage. As mentioned earlier in the data cleaning principles, you can combine multiple traces, and you do this using that calc average trace function. So to do that, you'll use it within the evaluate option. So I have an example of what that line of code might look like here. So we've got our first stage 2-meter temperature variable that we defined in stage 1, and then a second temperature trace, for example, from a nearby climate station, or if you had another of your own sites nearby. And then this function regresses these two variables and uses the linear fit to fill gaps in the first variable. And I'll show you where this would go. So here's an example of how you would incorporate that line. And you'd need to name this the same name as in your first, what you named it in the first stage. So once you're happy with the second stage ini, you can then run the second stage. The only difference is when you run this command, you want to have a 2 here to represent the second stage instead of a 1. So now on to the third stage. So of all the 3 stages, the third stage generally requires the least amount of work, but is usually the most computationally sort of intensive, as it includes running models for gap filling fluxes. And so you would add your site metadata to the site-specific configuration file provided by us, and I'll go through that with you. Most of the settings for the third stage are in a global configuration file that's obtained on your computer during the directory setup. Again, you shouldn't edit this file directly, but you can update and override settings if needed in this site-specific file here. So just a note on gap filling methane flux. The predictors for the random forest models are currently all set to these variables. So shortwave radiation, air temperature, and vapor pressure deficit. But for the methane flux, we're recommending that the inputs should prioritize soil variables, such as soil temperature, soil moisture, and water table depth. And so you would change these within that site-specific config file, and it would look something like this right outside. And you can also change the predictors for other variables. This advice is just specifically for the methane flux. So then once you're happy with that, you again run this function, but instead of a 1 or a 2, you're actually going to not put a 3, but you're going to put a 7. This is a legacy artifact. So that's what you put to run the third stage. And then, yeah, just a reminder to inspect your data at each stage using the visualization tools provided. And then once you're happy with your ini and configuration files and their output, you can convert the data to a CSV file formatted for AmeriFlux submission. And the way you do that is the same command again, but instead you'd write an 8. So the 8 is for the AmeriFlux conversion. And then very conveniently, this command you can also use for running multiple stages. So this is how I would run all of those stages that we've just talked about, first, second, third, AmeriFlux. And you can also add multiple years and sites, and that's what that syntax would look like for that. So here I've just put again a sort of summary of the steps, really just for your reference. Yeah, so you can come back and look at that. I won't read it through again. Yeah.
I guess all of the ME file edits, so you would edit in some kind of like text editor,
Yes.
and then the commands that you run are in MATLAB to run /save.
Exactly, yeah.
You can edit them directly in MATLAB, it's
Yeah.
just so much easier to use something better.
And it's
But
nice.
like for a quick thing, like it's easy enough to just open it in MATLAB and edit it. They are essentially MATLAB files, they just don't have a .NET.
All right, so that's it for me for a moment. I'm going to pass to Paul and Sarah, who are going to talk about the data visualization tools. Let me just
Great. Paul, you can take it away.
Yeah, can you see my screen?
Yes, yeah.
Okay, perfect. Okay, so yeah, if you're following along with the online documentation, once you're done section 5 or later, there should be data in your database that you can visualize. So one way you do that is with the plot app. So to access that from the command window, you just type in plotApp, the capital A. It's all case sensitive in MATLAB. Type that in, press enter, and then sometimes it takes longer than others. Sometimes just wait a bit, and then this window should pop up, which allows you to find your data and plot it. So the first time you run it, these folder fields are going to be empty. On subsequent times that you run it, it'll remember the last successful time you did it and just keep that last one. Just give it a few seconds. The first time you run it, there'll be nothing there. You just need to navigate to your database folder. The easiest way to do that is with the GUI, just using the folder selection button. So your Windows Explorer or the Mac equivalent will pop up. And then you just need to find where that database folder is, the one that you set up from the earlier stages in the documentation. So I'll just find it on my system here. And so specifically, you want to select the database folder. If you select a different one, it's not going to work. Even if you go into that one and select one of the subfolders, you don't want to do that. It's not going to work. It has to be the database folder. So I'll select. Oops. Okay. For some reason, it just minimized the screen. So I selected that folder. And then what happens if you pick the right one? Any of the years that are available are going to auto-populate for the year. So if you want to look at the 2023 data, for example, then the site is going to auto-populate with any sites that we have in there. For the tutorial example, it should just show the TT site since you just have the one if you're working from the example data. And then if you've only done up to section 5 in the documentation, the data types should only be FLUXNet since you wouldn't have produced later stages, which then creates the clean data type. So don't worry if you're at those early stages and don't have a clean data, that's fine, it comes later. So we can just look in the Flux folder. And if you're at that initial stage of ingesting the data into the database, so all you have is the raw data, you're just checking to make sure that that process actually occurred, that you have data in your database, so you can just kind of flip through those. And so this isn't the tutorial data, so the variables that are here and what has data in it, what's not, it's not going to match perfectly with the tutorial version. So that can just be used to make sure that yes, there's data there, what it looks like. But then obviously you can look at things a little bit more closely, look at whether you have any gaps in your meteorological data that need to be filled. So just quickly switch over to the Met data here, pull up air temperature, because that's one that carries through to later stages for gap filling some of the flux data. So air temperature here. Yeah, so in that case, we have a big gap we want to fill. And then what we might want to do if we have alternate sources of data, so either other sensors at the same site, air temperature at nearby sites, we might want to evaluate whether those other sensors, first of all, have data for when we're missing data, or if they're from alternate, a little bit far away, so you're not quite sure whether it's appropriate to fill. You can always look at that. So if I want to check, I want one of the nearby sites for potential for gap filling. So this is a nearby site that obviously still has a few missing data points, but by and large fills in the data that we're looking to fill in. Qualitatively, they look pretty similar, but we have some trace analysis tools to go beyond just eyeballing the data. So if we wanted to compare those two traces directly, we can use the trace analysis tool drop down, and it's going to pop up this trace comparison tool, which is showing on the upper left just the residuals between those two traces at a half-hourly time scale of blue, and then daily averages of the residuals. So there's a bit of bias in the data. It's obviously more so at the half-hourly time step. So you can use some of this information to decide, is it good enough, or do you want to look for other sources of data? Clearly, if we're just looking for the whole data set, looking at the scatter plot between the two, it's got an R-squared of 9. So even though half-hourly maybe not perfect, it's probably good, and you're probably not going to get much better unless you have a co-located secondary sensor that you're looking to replace with. So just to highlight a few of the features of the trace comparison, it's this upper left panel that you can interact with. You can zoom in into shorter periods, and sorry, I just didn't notice if it actually updated. It should have updated. Okay, yeah. I just wasn't paying attention. If you zoom into a particular period, the other three panels are going to auto update just to represent the data that's visible in this upper left-hand figure. And all of those kind of summary statistics are also updating along with it, just to reflect the data that you're currently visualizing in this upper left panel. Then maybe quickly, just a couple of other things. So in addition to just looking, at your data for general quality assessment, whether you have gaps that you need to fill, whether spike removal needs to occur, you might just want to look at how your data is changing through the different stages. Obviously you can make mistakes and accidentally kill a whole bunch of data that you didn't intend to. So for example, if we want to look at the CO2 flux from the first stage, let's see. Oh, it's in a net, that's why. It's a flux variable. That makes sense. Yeah, so with the first stage, partly we're just getting rid of data that's clearly bad, but isn't super sophisticated in terms of removing bad data by using diagnostic data or other sources of information. It's just kind of min-max and simple spike detection. But if we want to compare it to later stages that take advantage of some of the other traces that you've collected, some of the diagnostic data, turbulence data, all that kind of stuff, we can do a much better job of cleaning the data. So we can see how going from stage 1 to stage 2, that it's much cleaner. Obviously, you're you're losing some data in the process. And then similarly, move from stage 2 to stage 3, where at least within the pipeline, if you go to NE, rather, you have additional data that's removed due to presumably you start filtering. And then you can look even further that once it's been filled in, where's the stage 3, that's fine, so in stage 3. NE, whether it's with the random forest model, so we have our gap fill data using the random forest model approach for gap filling the flux data, or the MDS. So this would be your final data set potentially if you're happy with all the choices that you've made. And then again, just to kind of highlight different ways that you might want to use the trace analysis tools, just for fun to see what some of the differences are between the 2 different gap filling methods. It's the exact same thing in principle in terms of what's happening here, showing the residuals between those 2 plots, both the half-hourly timescale and the daily average. So nice that the difference between them essentially is not distributed, but yeah, you can pick out differences, where, for example, nighttime fluxes seem to be similar, but there's a lot more difference in the daytime uptake. But yeah, it's just, an example to try to highlight some of the features of the plotting.
Great, thanks, Paul. So you'll have a chance to play with that throughout the upcoming sort of hands-on tutorial part of this. And then I'll just share and show another plotting tool that we use. We use this one to sort of visualize our data online so that others can access it, but you can run it locally as another way of visualizing your data. And it has some similar features to what Paul has, but it's written in R, so just a couple different options for folks. Okay. So, all right. So this is written, again, it's an RShiny app. You can run it locally to look at your own data, or you can host this on a website if you're interested in sharing your data more broadly. If you have multiple sites, which again, you can run with a single command line, you can put in multiple years and multiple sites. This allows you to visualize different traces. You can specify when you're running it, what level of cleaning you want. But for example, you can plot different traces here. So this is not through all the filtering stages yet. So it's there's some noise, as we can see, but you can zoom in, you can look at your data, you can change the date range up here. Let's go back. Yeah, there you go. So you can play around with the time. You can look at some various scatter plots. So you could look at the relationship, for example, between CO2 and methane flux. You can look at relationships for different years, see maybe how the relationship changes between years. And then you can also get some diagnostic plots. So you can look at, how tightly correlated are the 2 different variables. And then what's the slope of this line? And then how would it change for different years? So for example, if you're interested in looking at, so we look at shortwave in, there we go. You might want to make sure that your, radiation sensors aren't drifting. So you can look at, for example, shortwave versus PAR, and you can see how does it change between different years, maybe indicating, you might need a sensor back for recalibration. Here you can see that the R square doesn't really change between years, very, very small change in the slope. But if this were to drop, from one year to the next, it might give you some indication as to, some different corrections or calibrations your sensors might need. So you can look at the relationship between 2 variables. You can also look at diurnal cycles. So for example, here, you can look at the mean diurnal cycle for CO2 flux. You can get it for every month for your whole data set, or you can just zoom in, maybe do a couple days, or if you're worried about, a couple days of data, a couple weeks of data, you can zoom in on a select period. And then, lastly, you can look at the cross correlation between your potential radiation and your other radiation variables. So that would be shortwave in or PAR in. If you have multiple sensors, you might have multiple different ones you can specify here. But basically, similar to sort of the Ameriflex diagnostics, you want those two to overlap. If there's a pretty big lag, more than -1, it indicates that your time series might be off. So for example, if your data logger, wasn't set and it shifted during, the time from daylight savings to non-daylight savings time, you're going to see a shift there indicating that you'll need to shift the timestamp in your data set. And again, here, this is just looking at the cross correlation between the two. And again, you want this maximum lag to be, well, ideally 0, but not greater than -2 or not greater than -1. And then in black here, you sort of see the times when shortwave radiation in this case would exceed potential radiation, again, indicating that, maybe there's a slight tilt in your sensor and you might want to check that out. Okay, and you can also plot, again, if you have multiple sites, you could plot all years together. And then you can, again, compare. I deliberately sort of threw a little wrench in this site just so you could see, maybe there's an issue with this site here. And again, we're not through all the cleaning, so there's some noise, but it allows you to plot and compare multiple sites. So that's, again, another tool. We have some instructions on the website on how to adapt it to your own sites and your own data. But just another option here for you to explore and play with. Okay, Rosie.